Hello and welcome back to another episode of the Oxford Online Maths Club. I'm James and today I'm joined by Tarek.
Hi everybody. My name's Tarek. Happy to join James here today. I am doing my PhD in statistics and hoping to talk about some fun math today.
Excitingly, we're in the same place. Can we do the high five? We're in the same building for the first time in 3 or 4 years of doing these live streams. We're actually not on a Zoom call. We're giving that a go. How's it going at home? I hope you're all right, having a nice day. Let's do the poll for how was your day. As always, I'm looking at how people's day was at home. And while you're doing that, I'd like to plug Promise Europe again. I was talking to you about this before we went live. It's a summer school, it's 6 weeks long, it's in Oxford, it's loads of maths. It's really a lot of maths. If that's the sort of summer school that you're looking for, then you might be interested in Promise Europe. Applications are open until I think the 10th of March. And even if you're not eligible for Promise Europe, or even if you're not interested in Promise Europe, you might like their application problems. They have these really hard problems to try, where you, just thinking about their problems is probably fun. Good stuff. Yeah, so this is a graph of how was your day?
People having good days.
Yeah, I like that you can see chat as well, because you're in the same room. We're both here. Only one microphone to control. Brilliant. 70% are having a 5-star day, which I think is some sort of a record. I'm going to leave that going just to see if it does a regression to the mean thing. Ooh, stats. We named the episode 6 Degrees of Maths Club.
Okay, nice.
Because graph theory, right?
Yes, of course.
Because we're going to talk about graph theory. 6 Degrees is a reference to that thing about Kevin Bacon.
Mm-hmm.
Do you want to say it?
Ooh, okay, put me on the spot. I think the statement is, maybe not too technical, everybody in the world should be able to trace their connections to Kevin Bacon within 6 people.
Something like you know someone who knows someone who knows someone who knows someone who knows someone.
6 people. Eventually you can get to Kevin Bacon.
Kevin Bacon, in particular, who's an actor. I think people also count if somebody starred in a movie with Kevin Bacon.
Yes, I think
they count.
There's also the Erdős number.
Yeah, okay, so Erdős number, how does that work?
So this is the same concept, but with authorships. So if you write a mathematical paper and publish it, and it's how many people can you trace back to Paul Erdős, who was a very famous Hungarian mathematician. So I think like my supervisor, her Erdős number is like 2 or something. So eventually mine will be 3. But yeah.
Wow. I don't know what mine is because fluid dynamics quite far away.
It's probably less than 6.
Yeah. I guess that's the fact. Some people have a Bacon Erdős number,
yes,
which is where they've appeared in a film with n steps removed from Kevin Bacon and written a paper n steps removed from Paul Erdős. As far as I know, no one's got the other way round. They've written a paper with Kevin Bacon and appeared in a film with Erdős, but you know, there could be someone out there. Kevin Bacon, I think, counts as 0. I think we're counting from 0.
Yes, yeah.
Bacon number 0.
Bacon is 0. Yeah.
Kevin Bacon himself. Yeah. Good. People are having a great day. I forgot to check. Are you having?
What's your day like? An excellent day. Yeah.
Good. What have you been up to?
So PhD life. It's a lot of just being in my office working on. So I am doing statistical epidemiology as my subfield, and we do a lot of work with networks. So we look at the role that heterogeneities play in the spread of infectious disease in networks.
Okay, so like a disease, and then the network is some people, I guess, being near each other?
Yeah. So it's, if we're in the same room, maybe this is a bad example, but if we're in the same room and one of us is sick, we have a higher probability of infecting each other than maybe someone on the other side of the building. But we're both.
This is why we do them on Zoom. Right. Okay. I've mentioned Promise Europe. I think we should start talking about graphs, if that's all right with chat. Hi to people in chat, by the way. I didn't say hi to like Aya and Shrish. Somebody's asked, what's it like doing a PhD? Let's do that first. What is it like doing a PhD?
I like it. Yeah. So it's a lot of research. It's a lot of time management, but it's also really nice. It's collaborative. So I work with other people in my group. We have 4 or 5 people in my group. And then the statistics department is, maybe like 60 to 70 researchers, but there's also master students. There's also, I do some teaching for the undergrads. So it's really nice, sort of integrated environment. I have a really
when you say doing a lot of research,
yeah.
I imagine that's probably like reading a lot of papers?
It's mostly banging my head against the table, but no. Yeah, so it's mostly reading papers. It's there's a lot of coding that I do specifically for my the bit that I'm researching. But it's mostly finding new things that I sort of would like to know more about, understanding them, trying to use that in what I'm interested in.
Good. Okay. Cool. We've got to remember to look. We look at each other.
I know,
We've got to remember
but-
to look at them as well. we could do a podcast, and then we wouldn't have to look in a particular direction at all. There's a side project, right? Okay. Let's do some graphs.
Let's do it.
Okay. So you want to tell us about a fact about the number of friends that people have?
Yeah. Okay. So we're gonna call it the friendship paradox, and it will be clear why we call it that in a little while. Essentially, we're going to start from the premise that, on average, it is a mathematical fact that we will prove that your friends have more friends than you have. And I know that sounds quite sad, but maybe the fun of the maths will, will mitigate the sadness a little bit.
Well, I guess if it turns out to be true, then I don't need to feel bad about my friends being more popular than me, because you're going to prove that that's normal.
Exactly.
And not something to lose sleep over.
Yeah. Especially in an age when we're all so connected, on social media and stuff. And there's all this comparison. Comparison is the thief of joy, I believe, is the quote.
Oh, right. We do it for followers as well. Like the people you're following. I guess there's a bias there because it's not symmetric, right?
It's correlated.
It's correlated. The people I'm following have more followers? No, wait.
Yeah.
It's not quite symmetric, right? If I follow Stephen Fry, he doesn't have to follow me back.
Exactly. Yeah.
Okay, right. We'll think about directed graphs in a second. Okay. I see the Formula One usernames are back, and what timing you've chosen for that.
Okay.
Okay.
Should I start drawing the graph?
Let's draw this graph. You've got an example graph.
I do have an example graph, and I'll try to explain as I go along. But yeah, please stop me or anybody in chat. Please, if there's anything that you don't understand, just let us know.
Yeah, Miles has spotted the converse, right? That if your friends also experience the paradox,
this is why it's a bit paradoxical. Yeah.
Right? They should have more their friends, including you, should average to more. So that you have to imagine that they're friends with even more popular people, not you, and so on somehow.
I think maybe if we draw a graph,
Let's draw a graph
and explain some of the terms that we're talking about, average and friends, and I think it will make a bit more sense.
Cool. Okay.
So we're going to start with an empirical graph. So this is a graph that somebody found after doing a bit of research. So we'll start with Betty. Betty is one person in this social network, and we're going to have 8 people total in this network. We'll start with Betty as just an example. So Betty has one friend. Betty's friend is Sue. But Sue has 3 friends. So Sue is friends with Alice. Sue is also friends with Dale. And Sue is also friends with Pam. Okay, we'll expand the network a little bit to drive home the point, but for now, so when we talk about the number of friends that a person has, in this graph sort of network setup that we have, it's equivalent to looking at how many connections every name has. So we can say that Betty, can I change color? Oh, I can, okay. So Betty has one friend, right? Betty's friend is Sue. Sue has 4 friends, right? She's friends with Betty, but also Alice, Dale, and Pam. And now if we think about what we're interested in for the paradox, it's not just about how many friends you have, it's about how many friends your friends have on average. So if we go back to Betty and Sue, so Betty has one friend. So on average, Betty's friends have 4 friends, right? Because her only friend is Sue, so the average number of friends that Betty's friends have are 4.
Right, it's the average number of friends of my friends. So I need to go out and survey all of my friends. In this case, it's just sending a message to Sue. How many friends have you got, including me?
Including you, yes. Yeah.
If I'm Betty. So I want Sue to, and I'm going to add that up.
I'm trying to move. Oh yeah, okay.
Oh, look at this.
Excellent. Okay, but now if we expand the network a bit, I think maybe it will become a little bit clearer. So Alice is also friends. Oh, whoops. My color's right.
We've got an Alice in chat.
Do we?
I think Alice going to turn out to be a popular person?
Semi-popular, yeah.
Semi-popular.
Yeah.
There you go. Alex.
Actually, no. Alice is, yeah. Well, we'll see. Yeah.
We'll see. Yeah. You put Jane on the network, and you.
So Jane is friends with Alice and Dale. I forgot that Alice and Dale are also friends.
Oh.
Pam is friends with Carol, and Carol is friends with Tina. And Pam is also friends with Alice. It's hard to keep track of all your friends sometimes.
Okay, this looks, I guess, semi-realistic. I'm trying to imagine friendship groups that.
Yeah, so
I'm
you
in.
can imagine, right? Sue, Alice, Dale, and and Pam. They're all quite tight, but they also have some of their own friends who aren't necessarily friends with their other friends. I don't know. Yeah, it's quite.
You can imagine a situation where maybe this would
come
come
up.
up family relationships or something.
I mean,
There's a suggestion that we rename everyone on the graph. That's going to throw your.
yeah.
Some streamers would now auction off spots on the example graph to be like, hey, you could get involved. It's going to throw all your notes off, isn't it? If we change all the
not
names.
necessarily. We could change the names.
Can we put Aya on? Aya wants to be on the graph.
I want to
Can we
be on the
change
graph?
Pam to Aya?
Sure, yeah.
Rowan's judging people. I want to know what happens between. Well, it's about to be Aya, but there you go.
Aya, like that?
There you go. Yeah. Perfect.
Okay.
I want to know what happens between Aya and Dale because this is like
Rewrite your
really,
name so that
really
you can actually
close.
read it.
Really close.
Okay.
Cool. Okay.
Okay, alright, you're now on the graph. Hopefully
Something awkward happens at some point between Dale and the person currently Aya. Maybe Aya in chat can let me know.
Okay, so let's first go through maybe just how many friends everybody in the network has.
Okay.
So Jane has 2 connections, has 2 friends. Alice has 4 connections, also has 4 friends, like Sue. Dale has 3 friends. Aria, you also have 3 friends. Carol has 2, and Tina only has 1. Okay, but now it gets interesting if we start thinking about how many friends on average our friends have. So let's take, for example, Tina. Okay, Tina has 1 friend, Carol, and Carol has 2 friends. So the average number of friends that Tina's friends have is 2.
Okay.
Right? Pretty
And that's
simple. Yeah, just
Similar
like we
to
saw
Betty,
with Betty.
it's just
Exactly.
like polling one person.
Yeah. So now if we look at Carol, now we can actually do some averaging. So Carol has 2 friends, Aria and Tina. Aria has 3 friends, and Tina has 1 friend. So 3 plus 1 is 4, divided by the number of friends that Carol has is 2. So the average number of friends of Carol's friends is also 2.
3 plus 1 is 4. Welcome to Oxford Online Maths Club.
Gotta start somewhere,
Yeah.
Yeah. And if we continue in this way, it gets a little bit more complicated with these, this little sort of more connected graph up here, but it's the same calculation. Right? So Jane has 2 friends, Alice and Dale. Alice has 4 friends, Dale has 3 friends, so the average number of friends, of Jane's friends is 3.5. 4 plus 3, divided by 2, 7. Yeah, we can do the same for Dale. So Dale has 3 friends, Sue, Alice, and Jane. The sum of their friendships is 10. 10 divided by 3 is, well, I'll round to 3.3, but it's 3.3 repeating. Alice is friends with Dale and Sue and Jane and Aria, so that is 13 people. No, it's not. It's no, it is. Yeah.
Who are we counting? Alice with
Alice.
4 friends.
Alice has 4 friends: Dale,
so we've got
Jane, Sue, and Aria.
So you've got to add 7, 10, 12.
12. Yes. Okay.
Divided
I promise
by
I really
4?
do a PhD. Divided by 4 is 3.
Worst thing is people are playing along at home. Maybe we should let them try one.
Oh, okay. I really appreciate that, Miles. Thank you. I get a lot of judgment in the UK for my accent, and that's really sweet to hear. So yeah.
Right, chat's
Anyways.
going to do Sue for us. Chat's going to
that would be
chat's
great.
going to do
Let's do
Sue
that. Okay.
while we work out Aya's average of how many friends Aya's friends have got. But chat's going to tell me about Sue.
Okay, perfect. Let's do that.
Parallel processing.
This is amazing. Yes.
Okay.
Very efficient.
Aya's got 3 friends.
Yes.
Sue and Dale. No, I crossed it. Sue and Alice
And
Carol.
Yes.
Total. Sue and Alice really popular. 8 and Carol 2 points. So 10 divided by 3 is 3 and a third.
Yeah. So like Dale.
Okay.
Yeah.
Like Dale.
So 3 repeating. Yeah. And then Yeah.
So
We'll wait for
chat's
chat
going to
get
tell
back
us
to
there's a
us.
little bit of lag from our point of view between us
they're
saying
all
something.
doing
It's got to be broadcast to the internet. They've got to find a pencil. Then they've got to find chat. Oh, if you're joining for the first time ever, chat is at slido.com/OOMC. That's where you can do polls and things and get involved. Lets us know about our ability to add together small numbers. Hopefully someone in chat is going to tell us that they've added up 3 numbers. Here they come. I'm not sure. 11. We've got to vote for 11 divided by 4. And then there's a pause where I don't know if that's the right answer until somebody else tells me in chat. So we're going to wait.
Okay, yeah, that's great.
If you've got notes for this.
Well, maybe I will just make a quick comment. You mentioned directed graphs before.
Oh, yeah.
So one key thing we should say about this graph that we've drawn is that it's not directed. So maybe unrealistically, friendships are considered to be mutual in this graph. So if Betty's friends with Sue, then Sue, by definition of just how we've constructed the graph, is also friends with Betty. There are, there are types of graphs, where the direction matters. It's not necessarily mutual, but for our purposes now, I think we should just stick with considering mutual friendships.
I've seen those where people draw arrows and sometimes double-headed arrows for whether, and that's called a directed graph. That's not what we're doing today.
Yeah.
It came up because I mentioned Stephen Fry. Yeah, okay. 2 people in chat have backed up Oyster. Thank you, Alice and Trish, the Oyster. We've agreed now it's 2.75.
And I also agree with them.
Oh, yeah.
But I had a little bit more time to think about it. Yeah. Okay, great. So now we have a graph of friends. We've calculated how many friends each individual has, and we've also calculated the average number of friends their friends have. And sort of the way that the paradox works now that we have an empirical network is to look at the relationship between these numbers in red and these numbers in green for each of the individuals. So you'll see. Let's start with Carol, actually. So Carol is the sort of unique case where the number of friends she has, I can get another color, is actually equal to the average number of friends that her friends have. Okay, so maybe we can just we can have a little table here. So the relation, and when I say relation, I mean so either you can have the same number of friends as the average of your friends have. It's very confusing. You can have less than, so you can have less friends than the average number of your friends, or you can have more. Okay, all 3 possibilities exist, and we've sort of specifically chosen this network so that they're all there.
It's a kind of like a red number. The red number for how many friends you have
is less than, yes, yeah.
Okay. And green numbers for how many friends my friends have on average.
Exactly, yeah.
They might be more popular or less
That
popular.
makes a lot more sense, yeah.
Right.
And then this will just be a count. So Carol is the only one that has the same number of friends as the average of her friends. If we count up how many times the red number is actually less than the green number, we can see that it's true for Betty, it's true for Jane, it's true for Dale and Aria. Sorry, Aria. It's also true for Tina. And the only exceptions really are Sue and Alice up here. So we've got 5 people and we've got 2 people who actually have more friends than the average of their friends. And so this is sort of, it's the fact that this number is bigger. This number is bigger than that number. On average, in a social network, your friends are more likely to have more friends than you have.
That's amazing.
Yeah.
I mean, I sort of want to do, we shouldn't go and count this now, but I want to think about my friends of friends, like the next order of removed, because we could, on this little example, it's going to be painful, but I guess we'd be, what would we do to find like the average number of friends of friends? One step further?
You just go one further, yeah. So Betty is friends with Sue. Sue has 4 friends, and it's the average number of friends that Sue's friends have now. Is that what you're asking?
Yeah, I guess. I think I'm imagining. I'm not quite sure if this lines up with what I just said, but if you average the green numbers,
That's
so
we
we went from the red numbers for how many friends you've got to green numbers, the average number of friends your friends have got. If we average them again, maybe it gets even more extreme, but I'm not sure. I don't think we should do it. I think I might leave it as homework to investigate that thing that I think Miles mentioned a while ago, right? Like, if it's true that your friends have more friends than you, then shouldn't it be the case that your their friends of friends should be even more popular, because it's like the paradox twice, but that includes you. So
yeah,
if the paradox is true, maybe you should be bringing the average down. But oh my goodness, okay, that's a kind of homework exercise, I think, is to take the green numbers and calculate averages again, reading which way around that is. Are they bigger or smaller than the green numbers? Are they bigger or smaller than the red numbers? Right, sorry, I've distracted you.
No,
with
not
a
at
thing
all,
that's not in not in the plan. So that's the paradox.
This is sort of how research goes. You know, is you do something, it looks good, but then you think, oh, what if we did this other thing? What if we could consider something else? You know, and I think it's fun to do that. So we'll get into the maths and we'll sort of do this more formally. But essentially, why this is happening is because because the nature of the friendships, they're mutual, right? So if I'm friends with you, James, you're also my friend, and if James happens to be very, very popular, it is the case that when we consider everybody in the network, we're counting James more than once, right? We're counting all the people in the network. Many of the people have connections to James, so James is sort of overrepresented, if you will, in the degree distribution, which we'll get into.
Okay. Can't wait to learn about degree distribution. But as I see it in this graph, there's like Sue and Alice are the kind of super friendly people by the standards of this graph, right? They know 4 people each, with some overlaps, but they know 4 people each, and that means that if people are sending out these text messages to be like, tell me how many friends you've got, tell me how many friends you've got, I need it for a project. If I imagined, I think Betty sending that text message, and then later other people sending the text message, but the fact is that Sue receives that text loads of times because all of Sue's friends are getting in touch with Sue to ask how many friends Sue's got. So the kind of Sue's large number of peers contributes to this one and that one and that one and that one. Kind of reading it both ways around, I guess. Is what you're saying about it being symmetric.
And it just empirically makes sense, right? You're more likely to be friends with somebody who has a lot of friends. You know, if somebody is, very outgoing and likes to meet people, you're just statistically more likely to become friends with them. Whereas it's very unlikely that you will be friends with someone who only has one friend. It's just the nature of how we organize ourselves socially. But it's very counterintuitive. It's not,
Yeah, okay.
Because you think of friendship as a mutual thing, you know.
So question in chat about whether this is exceptions having a disproportionate effect, and I think it is a kind of, well, we're going to understand this in your maths that you're going to show us in terms of a kind of, I want to say weighted average.
Well, I mean, clearly it's not the case that for everybody, like you can't have it be the case where everybody on average there will always be some people who have more friends than the average, unless everybody has the same number of friends. That's sort of
let me run that back. Sorry. There must be some people with more friends than the average number of friends, because that's how the average works.
To live it in cases where everybody has the same everybody's friends with everybody else, so everybody has the same number of friends, and the average is the same for everybody else, and everybody ends up in this equal, right? But there are cases where, but there's always going to be at least a couple.
So there's someone in chat who says they don't have any friends, and they're anonymous, which is something you can do in Slido chat. This is why we use Slido instead of YouTube. This comment you would have to associate it to your Google account if we were on YouTube. But there's a point here that if you're a lonely point over here, anonymous, then there's some risk when we do this maths that we'll divide by 0, because we'll be doing something like adding up how many friends their friends have got and getting 0, and then dividing by
So this is one of the assumptions we make, is that we don't allow any of that to happen.
Okay.
We say we're not allowing anybody to have no friends. If you're being included in the network, it's a network of friends. You must have at least one connection, because exactly like you say, we'll end up dividing by 0, which is not fun.
We're not going to require that everyone's in the same kind of friendship group, though, I guess. So here, there's like a 4 degrees of Kevin Bacon thing. I've been counting on this graph. 4 degrees of, I guess, is it 4 degrees of Kevin Bacon? It's kind of 3 degrees of Sue, right?
Yeah.
Or is it 2 degrees of Aya? Look, it's 2 degrees of Aya, right? Everybody either is Aya, is friends with Aya,
somebody,
or is friends with somebody who's friends with Aya.
Mm-hmm. Yeah.
Yeah, I think I is like a Kevin Bacon of this network.
So this is yeah.
But that doesn't work. So that sort of 2 degrees of Aya doesn't work if I have like this disconnected bit over here. Even if anonymous like makes a friend, then these people are sort of disconnected from Aya.
Yeah.
Okay.
Yeah, we'll only consider sort of. Well, we call them this would be a subgraph if there were 2 of these. I don't know. Yeah.
Okay.
Maybe we should get into the graph.
Maybe we should do the graph theory.
Graph terminology now. Yeah. Okay.
Stop it.
So I'll just
Your popularity. Yeah. Sure, I will follow you down.
Below. Yeah. Okay. Okay, great. So we've been talking about graphs and networks, and that's all great. I think we all sort of have an intuitive sense of what that means. But because we are mathematicians, we like to define things rigorously. So we'll do that with graphs as well. So we'll consider a graph G. Oh, maybe I want to color. We'll consider a graph G to be a collection of what we'll call vertices and edges. Okay. So in the example we saw above, so V will be the set of people in the network that we're interested in. So in the case that we saw, this will be Betty and Sue and Alice and so on. Okay, all the people that we're considering. Excuse me. All the vertices. Another word used in graph theory is nodes. These are all interchangeable concepts. And then the other piece of the puzzle is this set of edges, E, and this defines the mutual friendships between the vertices, between the people in the network that we're considering. And so we'll write these just as sort of couples. So this is the friendship between Betty and Sue, but also the friendship between Sue and Alice, but also the friendship between Sue and Pam, so on. There's quite a few in this example.
But these edges are not. That's not all of the pairs.
No,
it's just the ones where they've got friends.
Exactly. Yeah. So you wouldn't have if we go back up to what we see. You wouldn't have a Betty Tina. Tuple, like that wouldn't appear. It's only where we've drawn the lines is what we call an edge in graph theoretic language. Yeah.
Got it. Okay. So your set of edges is fact about the graph of what things you've got. Good. Okay.
And the paradox, comes from when you write out. If we were to write out this full set E of all the friendships, you would see Sue and Alice be sort of overrepresented compared to the average. Right? You're only going to see Betty one time because you're only going to see Tina one time, but you're going to see Sue and Alice 8 times combined, which is why they
we've renamed Pam to Arya.
Oh, sorry, yeah. Sorry, Arya. I meant, yeah. There you go. Okay. Okay. So when we talk about sets, there's many things that we are interested in. One of the key things we're going to use this time is known as the cardinality of a set, or also known as maybe the size of a set. And this is basically, let's say you put the set of vertices of people into sort of these absolute bracket signs. We call this the cardinality of the set V, and it basically just means how many elements are in that set. So in this case, it's just counting up how many people we're considering in the network. So the cardinality of our vertex set is 8 in this case. And then we can do the same thing for edges. We can just count how many edges there are. And in this case, it's going to be 2, 3, 4, 5, 6, 7, 8, 9, 10. But maybe we can have them.
I can just quickly scroll
double check.
We're going to double count. Counting is not our strong suit.
Yeah.
2, 3, 4, 5, 6, 7, 8. It's like 9 on the page.
I think it's 10. 2, 3, 4, 5, 6, 7, 8, 9, 10.
Welcome back to Oxford Mathematicians Counting to 10. We're going with 10. That's already information, right? About just from these cardinality facts. Is there a fact here that you could work out the average number of friends from that? Am I mad?
No, it's exactly what we're going to do.
Okay, okay.
Yeah.
Okay.
So the first thing we're going to do is now to consider these red numbers, so the total number of friends that any given person has in the network, as a function of the size of these sets, of the how many vertices there are and how many edges there are. Okay, so let's call the average number of friends that any individual in the network has. Let's just call that mu. Okay, it's a good classic Greek number for averages. So if we think of mu as the average number of friends that an individual has in the network, how do we calculate that? Well, it's an average over the total number of people in the network. So in the denominator, we're going to have this size of v, right? You're going to think about how many friends do we have, and you're going to compare that to how many just total people there are in the network. Now, in the numerator, how do we think about... in the numerator, how do we think about collating all the information that we have in this graph into one sort of mathematical expression?
You're trying to do the average number of friends by...
that an individual has.
Okay, okay.
So essentially, if you just go back up to the graph that we saw and count up all the red numbers and divide by...
Yeah, so if I add up the red numbers, I get 20.
Mhm.
So if I add up how many friendships... Do I mean how many friendships? There's something odd here, isn't there? Because chat's probably spotted it already, but if you add the red numbers together, you get 20, and I think that's twice as many as the number of black lines joining people, because I've counted each one kind of twice, once from each point of view. Like the Betty-Sue relationship, I've counted it once as being one of Betty's friends, and I've counted it here as being one of Sue's friends. So if I add up the red numbers, I should get twice the number of edges.
Exactly right.
So that's helpful for our average mu, the average number of friends for the people in this graph, not counting this weird bit I added. So mu for the average of those red numbers. Okay.
Yeah, no, you're exactly right. So if we write this in terms of the size of these V and E sets, it's exactly like you say. It's 2 times the number of edges. So the number of edges tells me how many friendships there are total in the whole graph. And the reason that we have this 2 is exactly like you say, James, because every time you count an edge, you're actually counting it from both sides.
Yeah,
right?
I've seen things about counting handshakes before. Right, okay.
Yeah.
Times 2.
Yeah, so this accounts for all the friendships in any graph. And in our case, specifically what we see is, if we know, the size of E is 10 and the size of V is 8, that this is...
Ooh,
sorry.
I was labelling it. I'll do it over here.
Oh.
Sorry. Oh, you're putting the numbers in, right?
So then, we just plug in, always good to work with real numbers. And this comes out to 2.5. I can do that.
Okay.
Okay, so this tells me that on average for the network that we've drawn, the average number of friends that any individual has is 2.5. Okay. Now the next bit is a little bit trickier. We want to think about, how can we come up with an analogous mathematical expression for the number of friends that my friends, that an individual's friends have on average across the graph.
Right, so this is the average of those green numbers that we calculated.
Mm-hmm.
It's the average of... Okay, the average... For each individual, we're working out the average number of friends that they've got, and then you're going to try and average that across all of the people.
I'm not just going to try it, we're going to do it.
Okay. Whoa. Love the confidence. This is a calculation we didn't quite do. We've said. So the green numbers, we saw that some of them were higher than the red numbers.
Mm-hmm.
Didn't actually work out the average of them back up there, but I guess we can go and check it.
We can do that. Yeah.
Maybe you're going to make a formula or something that we can check. Let's go. Okay.
Yeah. Okay. So maybe one other aspect of graph theory we should introduce is the degree of a node.
Sure.
This will be, I maybe forgot to do this. I'm sorry. So in any graph, the degree of a vertex or a node or a person, in our case, is the exact same, has the same definition as the number of friends.
Mm-hmm.
So because Yeah. So Tina's degree in sort of this mathematical graph theoretical language is 1. So it's the same as the number of friends. It's just how many times she's connected to someone else in the graph. So yeah, actually they are interchangeable in this case, degree and friendships, when speaking about an individual. But it gets, when we talk about friends of friends, this notion of degree is a little bit more abstract, is maybe a little bit more useful than saying friends of friends over and over again.
Yeah, okay. Average degree is something I can say.
That makes
average.
sense, yeah.
Average number of friends is too many words. Okay. Oh, that's annoying because it's the word degree again, which people already use for angles and for degree of polynomials as a thing, and people use for the qualifications you get from universities, and people use it when people say 6 degrees of Kevin Bacon or 6 degrees of Maths Club. They don't mean that sort of degree. They mean the steps removed. So maybe we're, as a community, using degree for too many things, but we're going to try and use it just for number of friends, number of things you're connected to directly connected to in the graph.
Okay. So there's 2 steps to doing this calculation. Okay, we're interested in the average number of friends of an individual in the network. Maybe we should write that down. So this is what we're going to compare mu to at the end. Okay, so average number of friends of an individual in the graph. Exactly like you say, this is the average of those green numbers that we saw before. Okay, so calculating this thing might seem really complex on the face of it, but really we can just break it down into 2 steps. Okay, so step 1, we're going to look at how do we choose an edge or a friendship from the graph. Okay, so first we have to choose a friendship, and maybe we can use some set theoretical stuff. So we can choose an element E in E. Okay, it's just one edge that exists in the set of all the edges of the graph. And then step 2 will be to calculate the degree, the number of friendships of that chosen E.
Wait, I thought degree was...
Of that individual.
Sorry.
Yeah.
Okay.
Yeah. So you choose, if we have our network, we choose one edge. That edge has 2 people that it's connected to. We choose one, and then we calculate how many friends they have.
Okay.
And if we do this uniformly at random, we end up with the average number of friends of our friends.
Oh wow. Okay, so you're going to look at all of the edges, because those are the things that count as friendships, and add up when that friendship is invoked. You're going to look at the degrees maybe of both sides, or maybe just one side or the other.
We're going to do one side.
One side,
and
okay.
Maybe we can talk about probability. Maybe this will make a little bit more sense.
Okay. Right. Let's do it. That's the plan, I think.
Okay.
So look at random edges.
Yeah. Okay. So what's the probability? I'm going to write it as this P. There's a lot of different notation for probability, but I like this one. So what's the probability of choosing an individual, choosing a person in our network, choosing a specific vertex, and I'll write little v is an element of the whole set of vertices of people. Okay? Well, it's how likely are we to choose a given edge that contains any vertex in the whole graph?
I see, because your strategy is to choose an edge and then pick one of the people on it.
Yeah.
So some people are going to get sampled more frequently than others. It's not just 1 in 8, because your strategy of picking people is not fair across the people.
It's not. It doesn't conform to the actual underlying distribution of the.
Right. Okay. Can we get chat involved here? We're thinking about this weird way of choosing people, which is to pick one of the edges at random and look at one person involved in that friendship and think about, okay, what's the probability that I get Aya after doing that process.
Mm-hmm.
I chose a random edge, I picked one of the people involved on that edge, and I got Aya. Oh, how often does that happen?
So
Okay.
it's the degree of the vertex that you choose.
Something
So
to do.
the number of connections that the chosen vertex has. So if you have more connections, this number will be higher, right?
Okay,
This is
yep.
where it comes from. And then you just divide by the total number of edges that exist in the network. That is the probability. That's how likely a given edge contains our vertex V.
Okay. So am I looking at both ends of the edge?
So
or-
then to get rid of that problem, you just multiply by 1/2.
Oh, thank goodness.
Yeah, yeah.
You left me hanging there.
Yeah.
Okay.
So
So kind
multiply-
of counting. Yeah. Okay. So this strategy of picking people. Yeah, I also agree with chat here. I don't quite see yet how that's going to give us the average number of friends, but I think we'll get there in a second.
So this is just part one. This isn't actually how you do the calculation yet. This
Okay.
is just we need this bit to use in the next step, which it will be calculating the degree. So first we have to choose a vertex, right, randomly, and then we want to take the friends of that vertex and then do the expected number, the expected value.
Okay. Let me just scroll back up for the graph. Hello, person who just joined us, and also a recap for everyone else. We're looking at friendship networks and the fact that your friends tends to have more friends than you do. We're thinking about this method we're going to need for probability, a sort of probability way of choosing people, where to choose someone at random from the graph, instead of just picking them uniformly, we're going to pick one of the edges, bam, and then choose one of the endpoints on that edge. And the probability that I get Aya when I choose one edge and choose one endpoint is something to do with how many endpoints there are at Aya. That's the degree of that node, or the number of friends that Aya's got, 3, and also something to do with just how many edges there are overall. There's 10 edges on the picture, so 20 ends of edges, 3 of which belong to Aya. So if my strategy is choose a random edge and then pick one end of it, then it's kind of the probability I get Aya is 3, the degree of that vertex, divided by 2 times the number of edges. That's my 1 minute recap of what we've done so far.
No, it's exactly, yeah.
Okay,
It's
done
exactly
that. Okay.
Yeah. Okay, so now we know what the probability of choosing a given vertex is, choosing a person. So now what we want to do is calculate the expected value of the friends of that randomly chosen vertex. Okay, so I'm just going to write this in plain language. So what is the expected number of friends of a randomly chosen, it's doing that spline thing you were talking about, randomly chosen friend.
Ooh, hang on. So a randomly chosen friend. Do you mean using the method from just above, or what's a?
So key to this discussion is that there is a relationship between friends and friendships, right? Every friendship is defined uniquely by 2 vertices, but it's not the converse, right? Not every vertex is uniquely defined by a friendship, because you have some people who have multiple, whose degree is bigger than 1, right?
Okay.
So
chat says, is that just equal to mu?
no, it's not. If it was, then there wouldn't be much of a paradox, would it?
Okay, I need to understand. I think the key is for me to understand this randomly chosen friend. Then,
Okay.
Tell me more about what's going on there.
This is exactly what we did with the probability. So the way that we've set this up, step 1 is to choose. Maybe I should have wrote V and V, but like I said, you're choosing a vertex, you're choosing a person, but we want to do this. We want to do this randomly. We want to do this in a way that doesn't bias towards certain people. We just want, if I have the network, what's the odds? What's the probability that I choose a given person? Well, that's going to depend on how many connections they have. So one way to do it, there are other ways to do it. One way we've decided to do it is to first go for a given edge in the graph, and then say, okay, that edge has 2 ends. I don't want to choose 2 people, I only want to choose 1, so we multiply by this factor of 1/2.
I see. Okay, so I should do some sort of for expectation, because you're now asking me for an expected value, I should do some sort of adding, some sort of sum, because I know for expected value you're supposed to take all of the possible outcomes and multiply them by their probabilities and add that up. So okay, there's a sigma for summing. We're good.
So let's do that. So let's take all of the values, and I'm going to write D instead of degree, but they mean the same thing.
Sure. So maybe I get Alice, maybe I get Aya, and then I read off what's the number of friends that person has got. I did my random process thing up there, random process to find somebody, and this is the probability that I hit Aya or somebody.
Yeah.
That's the probability I hit Aya in brackets, and then when I see Aya, I say, oh, how many friends have you got? And that's D of V, the degree of that particular vertex.
And if we do this process over and over again for all of the people in our network, for all of the vertices in our set of vertices, we arrive at this expression for the expected value of friends of a randomly chosen friend.
Okay, so it's kind of like, let me flip it. So before I was imagining that each person was going to send text messages to find out the number of friends their friends had, because they were going to do that sum.
Mm-hmm.
This is like if I'm the FBI and I'm tracking all of that. I've got all of the text messages.
Yes,
right?
you know everything.
If you imagine for a moment,
yes,
I know you know everything, but there's so much data that I've just got to pick a random text message and just see, aha, it's Pam texting Sue to say that Pam's got 4 friends.
Mm-hmm.
Interesting information. I'll write that down. And then this average here is the average that. Well, it's the average that everyone's calculating, right? It's the average of the number of friends they've got, because that's what the text messages are about. But when I grab random text messages, I'm more likely to get text messages being sent by popular people, because they have to tell everyone how many friends they've got.
And all of their friends,
I guess,
include them.
Yeah, sure. So that their text messages are frequent. That's what this bracket says. The probability that I get text sent by Aya is pretty high, because Aya's got to text all of their friends. And then the content of that text message is also high, because the text message says basically I've got lots of friends.
Yes.
I guess there's kind of a D squared going on in here. One of them because you're sending lots of text messages if you're popular, and one of them because your text messages have large numbers in if you're popular.
Yeah.
Okay, I'm getting there, I think.
And it's a good maybe analogy that you made, or I don't know, setup that you have with the FBI, because all of these calculations rely on us having complete knowledge about the entire network, and that's sort of where the paradox sort of aspect of it comes in, is because we usually don't actually know how many friends our friends have exactly. You know what I mean? And so this is why actually, if you ask people, do you think your friends have more friends than you do, or do you think you have more friends? Most people actually respond that they think they have more friends, because they don't have a perfect, complete view of, and it's very unintuitive. Like, yeah, this is not straightforward stuff at all. And you're helping very much to try and explain.
I've remembered that I'm British. I've remembered that I'm British. I should have said GCHQ all the way through. Right. Okay. This is an interesting sum. It's a sum. I love that you've got. By the way, the sum where people might have seen a sum that goes over whole numbers, like n equals 1, 2, 3. Here, the things we're summing over are people. So you've said that you've got to sum over the different V's are the different people, and this is how you've written it, like V in the set of V. I like that. Yeah. Nice sum. I don't have any intuition for how large it is.
So we can maybe just rewrite it quickly. So there's stuff that's inside the sum that actually is not dependent on the thing that we're summing over. So we're summing over how many people there are in the network, but actually the total number of edges is irrelevant. It is not related to that, to summing over the individual elements of the people.
Move 1/2 out of the sum.
And the 1/2 as well, yeah. So we can bring out 1 over 2 times the total number of edges, and what we're left with is the number of people summed over, and it's the degree squared. Okay, but now this is a very interesting property. This is a very interesting sum. Are people familiar with the concept of variance?
Let's ask them.
Okay,
Are people familiar with, so I don't know how much probability you've done at school yet. Maybe you've seen averages like mu. Maybe you've seen variance or standard deviation or something like sigma squared or something like that. Have people seen this? Let us know in chat. Zoe's first in chat, and Zoe says yes. So it's very tempting for me to go, brilliant. I would like, if people are watching home thinking, saying, I don't know what standard deviation is, then maybe this is, you will learn at some point about standard deviation. Yes, we got an anonymous note, which is one of the lovely things about anonymous. The standard deviation measures the spread around the average. There's a formula for it in A level, which I think you're about to invoke, and I think you should do it.
Okay, so I'm going to describe it in terms of graph theory, but maybe you can help me bridge the gap between what they've seen.
Okay, you do the graph theory.
Yeah.
I'll translate into A level stats, and
Okay.
also teach two. I'm teaching two people A level stats at the same time. Okay, that's not wrong. We've got 10 minutes.
Okay.
No, this is a good 10 minute. This is 10
jeez,
minutes.
Okay.
No,
Okay.
we're good.
So variance, as James says, is a measure of spread in a population. So in terms of graph theory, it's a sum over the edges. It's a sum of the degrees over the edges squared, divided by the total number of vertices in the graph, the total number of people that we're considering. So this is known as the variance. And then in terms, this is mu squared plus sigma squared, and sigma squared is known as the variance.
Wait, that's
So,
the
yeah,
definition
sorry,
of sigma squared.
Yeah, oops.
Oh, I see.
Right,
It's the variance if you subtract mu squared.
Exactly, yeah.
People doing A level will have seen maybe the expectation of x being the average value, mu, and maybe they've seen the expectation value of x squared, like how large is x squared. There's this quantity where you do the expected value of x squared and subtract the mean squared. That's called variance, and that's the same formula as this, right? This first thing is the average of something squared, and I guess you're subtracting mu squared to get the variance squared. Okay, cool. If I've moved the minus mu squared onto the left-hand side, that's variance.
Makes sense.
I'm considering teaching A-level stats, but I think I should not teach too much A-level stats. Giving an impression of A-level stats. This is a thing to measure the amount that your distribution is spread out around the mean. If you see a bell-shaped graph with some average in the middle, but there's some spread. It might be wide, it might be narrow. That's a measure of standard deviation or variance.
Exactly, yeah.
Okay.
And so the key bit is that this sigma squared value, the variance in the degree distribution of the network is only 0 if all of the people have an equal number of degrees. If all of the friendships are symmetrical across the entire network, which tends to not be the case in real social networks, is sort of why this paradox is a thing.
Sure, so generally this sigma squared is not 0, right?
Exactly, yeah.
That's about having this equal 0.
Sorry,
But okay.
Yeah.
In general.
And particularly because it's the square of a number, it's positive. So maybe I'll write that,
okay.
Yeah.
Right, so this sigma squared thing is normally not 0, unless your data is very special. And because it's a square thing. It's the sum of loads of squares, right? Well, I guess minus mu squared. Homework, it's positive. You can call it sigma squared. It's a positive number. Okay. That's very similar to the thing, I guess this formula for variance is very similar to the thing in your question.
Yeah. So if we accept this as a definition of variance, which, maybe I shouldn't ask you to do, maybe you should make sure on your own. But if we do, then what we can do from here is say, okay, I have a sum of the square of the degrees, and I know that the square of the degrees divided by the total number of degrees is equal to the average, the sum of the squares of the average and the standard deviation. So then I can use this relationship to rewrite this equation here, 1/2 times the absolute value of E as 1/2 times the total number of edges times the total number of vertices times mu squared plus sigma squared. Okay, so that's just using this relationship that we know exists between the average and the variance and the degree distribution of a graph. Okay, it's been a long time now, but if you go all the way back to the way that we
we've seen this
define mu, Maybe I'll just write it again so people don't have to go back and forth.
What's up here is 2e over v.
Yeah, so mu, actually we know, is 2 times e over v. Okay, we know that. We showed that was the case. But we see a v over 2e. So this all boils down to 1 over mu. And what we're left with is 1 over mu times mu squared plus sigma squared. We can simplify that a little bit to mu plus sigma squared over mu.
Right.
And the key bit here is that this is strictly less than mu, which is the average number of friends.
Bigger than mu. Strictly bigger than mu.
Say it again.
Bigger than mu,
Oh,
right?
yeah,
Rewind slightly. The really key thing is that
this number is bigger than mu.
Nice.
It's the average number of friends that your friends have, plus some variance, which describes the spread of total number of friendships across the network, which is generally not 0. And I think Srisht, I hope I'm saying that right, has it right. If the graph was fully connected, there would be no variance. Everybody would have the exact same number of degree of whatever. Would have the same degree. Would have the same number of friends. Would have the same, and that sigma squared term would be 0.
So in this tiny little doodle here, everybody's got 3 friends. So the average number of their friends is also 3. But this is a case where these numbers 3, 3, 3, 3 has no variance.
Yeah.
So I love this formula because not only is it a little proof that the average of your friends is larger than the average, like what we expect your personally, how many friends you've got, but also it quantifies it to give you that it's something to do with the variance.
Yeah, so in particular, the higher the variance, the more skewed, the further away the average number of friends is from the average number of friends of your friends.
Right.
Okay. So you can imagine an extreme case where one person has millions of friends, and all the individual people only have that one friend. Well, then the average is going to be quite high, but that's very skewed by this one person that has very, very high degree. In other words, this sigma squared term becomes very large.
Yeah.
But the average number that every person has doesn't scale that way. Yeah.
Right. Just to clarify the expectations and averages, there are a lot. In summary, mu is the just average of the degrees of your graph. Each graph has got a particular degree for how many friends it's got. Mu is just the average expected value of that. I guess that's expected value of the number of friends that you've got. Or maybe would you ever say E of D for degree?
Yeah. I mean, in this case, it is the same. The degree is the number of friends that
okay.
Yeah.
And that's called mu. But then we've got this second one, which is the expectation of something more complicated that you've written in words, which is the expected number of friends of a randomly chosen friend. We're doing a kind of kind of one big average, because averages are linear.
Exactly.
But you can think of it as a kind of 2-step average if you like. Firstly, calculate these green averages for each person. So like Dale goes out, averages these 3 numbers, adds them all up and divides by 3. And then the calculation we've done is for the average of these green numbers. I'm really not brave enough to add these green numbers together. Oh, you can't just say that sort of thing though, can you? 1 minute of calculation. Okay, so the red numbers average to 2.75. That's mu in here. And then the next one averages to 4, 7 and a third, 9 and a third, 11 and a third. Why am I doing this? 14 and a third. Call it 15, 16, 17, 18 and a third, 19, 20, 23 and about 24 divided by 8. So the expected value of friends of friends is about 3, I think. And there's a formula for calculating it below, where we're supposed to take, instead of actually averaging the green numbers, the thing that we can do is to sum the degrees squared and divide by twice the edges. Which, you've got a calculator up. I was going to try and do it.
Please, yeah.
So if I sum the degrees, if I find the average degrees squared, plus 3 squared plus 3 squared plus 1 squared plus 4 squared plus 4 squared plus 2 squared. And I'm supposed to divide this by v or something? Yeah, divide this by 8. The plan is that this turns out to be exactly 3 and then we all go home. Shrista's got about 3. But then I've got more adding to do, right? 10, 20, 4 and 16 is another 20, 4 and 16 is another 20, so this is 60 divided by 8, that's way too much. Was there a factor of 2 in there as well? There's a factor of 2 in there, isn't there?
Because every edge has
there's a factor of 2.
2 vertices. Yeah.
60 over 16, I'm still way too large. 30. No, I'm not.
I think it's right.
Okay. Cool. Is it about 4? I can't add. 10. You're looking it up in the paper, right? Okay. Right, good.
It's
averages.
Yeah, well, we should be doing this with the green numbers.
The green numbers?
Not with the red numbers.
No, with the red numbers. I thought red numbers are...
friends.
Ah.
Yeah. But
yeah, okay, right.
Yeah.
I've done a stupid calculation and maybe done it wrong. What an on-brand way for me to finish. That happens a lot. Good, right, okay. We've got a formula for a kind of distribution like that. There's some exceptional cases, some interesting kind of spare cases.
Yes, so...
we maybe put in which I might put in the further reading notes.
Okay, yeah.
I think. So there's some exceptions like this, where everything's average. And then because these are average statements, not statements about counting like the mean or not statements about like the median experience. You can create some special exceptional graphs where the averages are like that, but the most popular experience happens to be the other way around. It's difficult because the average of the green numbers has to be higher than the average of the red numbers, but you can just make the graph, just tweak it so that they it works out the other way around.
Exercise they could try it out. See if they can
let's do it as an exercise.
Yeah.
There's a simple graph with 6 vertices, let's say. There's an example with 6 vertices and not that many connections between them, where most people have more friends than their friends do.
Yeah.
Okay, good. Tarek, thank you very much for being on
Thanks
the
so much
live
for
stream.
having me. It's been so
Thanks
fun.
for coming
Yeah.
and proving friendship paradox. Don't get that every week. I think we're going to wrap up there. If you want to find more about the Maths Club, we've got a website which is on screen, maths.ox.act.uk/club, which is also where you can find about 80 previous episodes over the last 3 years, none with 2 people in the same room though. It's also where you can find the further reading. We make some extra notes available after the episode based on things we forgot to say or things we want to give you as extra work to try. If you want to see more of this show, we're back next Thursday in 167 hours for another episode of the Oxford Online Maths Club. But I think we'll say goodbye. Thanks for watching.
Bye, everybody.
I can't remember where the button is.
Tell your friends.
Tell your friends because your friends have yes.
There's one thing to take away.